Houston, we have a problem. A phrase that wasn't followed by a movie-style pause, but by a very real chance of never making it home. In this episode, how Apollo 13, after the explosion of an oxygen tank, turned into a fight for air, warmth, and time, and how the crew, together with engineers on Earth, assembled a rescue out of whatever they had at hand. A pop and silence. This is not a cinematic explosion. No fireball, no shaking camera, it's a pop. As if someone in the next room dropped a heavy wardrobe, and immediately, a strange silence inside the sound. The hum changes, the instruments blink differently, and somewhere deep inside the ship a new, wrong kind of life begins. Jim Lovell looks at the panel. Fred Hayes turns his head, listening, as if you could hear exactly where it broke. Jack Swigert, on radio duty today, says a sentence that makes coffee go cold in people's mugs down on Earth. Houston, we have a problem. More precisely, almost word for word. Okay, Houston, we've had a problem here. The words sound calm, too calm for what's happening on board. Because in space, calm is not always a sign of control. Sometimes it's simply the only way to keep panic out. And then the story begins, where everything hangs on a single decision, not a pretty one, not a heroic one, a cold engineering decision, a decision that has to be made fast, and made correctly. Because the price of a mistake here isn't mission failure. The price of a mistake is not coming back. What the perfect mission was supposed to look like. Apollo 13 was heading to the moon, not as the first, and not as the last. That's an important detail. The first is always special. The first has more romance, more political tension, more we must. Apollo 13 was a mission where a lot had already become routine. The Saturn V rocket, a proven machine, the command module, a home where everything is familiar, the lunar module, a workhorse for descent. The plan was simple: enter lunar orbit, land in the Fra Mauro region, carry out the scientific program, lift off, dock, return. That simplicity is deceptive, because in space, simple means only one thing. You've already written out thousands of steps, and you're hoping each one happens on time. And now, a couple of days after launch, the system says, no. This is not what a minor malfunction looks like. Voltage in the electrical system, pressure in the oxygen tanks, readouts from the fuel cells. A key fact the listener needs to understand. On the Apollo spacecraft, much of the in-flight electricity came from fuel cells. They ran on oxygen and hydrogen, producing electricity and water. So oxygen isn't only what you breathe, it's also what the ship lives on. And now the telemetry shows the impossible. Pressure in one oxygen tank is dropping, the other is behaving strangely. Through a window, they'll see what becomes the most terrifying image of the mission: a cloud streaming out of the service module, like a pale jet spreading into the black vacuum. This is not smoke, it's oxygen leaking into space. The ship is losing a resource as if a hole has opened in its side, only not in the hull, but in the life system itself. In that moment, you understand one simple thing. The moon has stopped being the goal. The moon has become the background. There is only one goal now: Earth. The room where everyone breathes together. We move to Houston, to mission control. There's no yelling there. There is discipline. The flight director and systems engineers stare at the telemetry as if it were a patient on an operating table. Every parameter is pressure. Every indicator is a pulse. And the worst part is not it broke. The worst part is it's still breaking. Because an oxygen leak means the fuel cells will soon start to die, one after another. Without them, the command module Odyssey will lose power. And without power, you lose navigation, communications, temperature control, life support. The crew has no right to long deliberation, but they have no right to rush either. Any action is irreversible. Shut a system down, and you may not be able to bring it back. Burn through the batteries. And there'll be nothing left to power the ship during re-entry. And now we come to the main crossroads. One thought that's terrifying to say out loud. There is a second ship on board. Not exactly a ship, a module. The lunar module Aquarius. It was supposed to be a taxi to the lunar surface and back. It wasn't designed for 3 people for long. It was designed for 2, and for a limited time. But right now, it's the only space on board that has its own batteries, its own oxygen supply, its own life support systems. and someone in Houston says an idea that sounds almost sacrilegious for the lunar program. Use the lunar module as a lifeboat. That suggestion is like turning the wheel on ice, because it immediately means several terrifying things. 1. The command module will have to be almost completely powered down to preserve its batteries for the return and atmospheric entry. 2. 3 people will have to live inside a lunar module designed for 2. 3. Water and energy reserves will become critical. 4. The return will depend on a trajectory and on maneuvering accuracy. Maneuvers performed on a system never intended for that role. But the alternative? The alternative is worse. The alternative is staying in Odyssey while it slowly loses oxygen and electricity, turning into a cold capsule. This is the moment when the choice stops being better, worse. It becomes possible, impossible. Free return. There's one engineering trick viewers rarely think about. It's called a free return trajectory. In simple terms, it's a path where the spacecraft, after looping around the moon, naturally returns to Earth, almost like a thrown stone that arcs around a hill and falls back. It isn't magic, it's gravity. In some missions, that trajectory is used as insurance. If something happens to the engine after heading toward the moon, the crew can still swing around the moon and come home. Apollo 13 ended up close to that insurance, and that sharply increased the odds. But close doesn't mean exact. And even on a free return path, you may need a correction to hit the right re-entry corridor into Earth's atmosphere. Too steep, you burn up. Too shallow, you skip off into space. So gravity gives you a chance, but it doesn't guarantee rescue. And that chance has to be held onto with decisions, on board and on the ground. The move. The decision is made. Move into the lunar module. To the ear, it might sound simple. They move to another compartment. In reality, it's a life transplant, because they have to. Keep communications and navigation, move the people and some of the equipment, avoid wasting extra energy, and at the same time, not kill the command module for good, because they'll still need it for re-entry. The crew begins to close up Odyssey. They shut down systems that are normally never shut down for long in flight. Psychologically, it's heavy. You're turning the lights off in your home, knowing you'll have to turn them back on, and there will be no time for mistakes. The lunar module Aquarius comes alive as a temporary shelter. Systems power up, instruments show pressure, air, electricity. And here, for the first time, a strange relief appears. They are not dying right now, but the relief lasts seconds, because the next thought arrives immediately. Aquarius wasn't built for this. Supplies are limited. They have to economize everything: energy, water, heat. The ship stops being a mission to the moon. The ship becomes a drifting ice floe, and they have to hold out on it until shore. How much time do they have? And here we come to the numbers that start to run people. How much oxygen is left in the lunar module? How much water? How much electricity? How fast does all of it melt away when there aren't 2 people inside anymore, but 3? And even scarier, how are they going to sleep, eat, and breathe when the spacecraft starts to cool down? Because saving power means saving heat. And ahead lies another invisible killer: carbon dioxide. The filters in the lunar module are designed for 2. And when CO2 starts to rise, the crew will have time for one decision, and for a very strange engineering trick. But before that, they have to do the main thing: swing around the moon and make sure the trajectory really leads home. In the next part, we'll go through the first, harshest day of survival, how they counted every watt and every sip of water, why it got as cold as a refrigerator, and what maneuver made the return possible not in theory, but in practice. The ship is dying of air. After the pop, everything on board doesn't happen in one blow, but in a chain. Oxygen leaks, meaning the fuel cells lose their supply. The fuel cells die, meaning the command module loses electricity and the water the cells produced as a byproduct. Power drops, meaning navigation, communications, heating, fans. Everything starts living off the leftovers. It isn't beautiful, it's mathematical. In the telemetry, you can see your future shrinking. And then comes the first main decision that holds the whole plot together. Power down the command module almost completely. Save its batteries for the return, because Odyssey will be needed at the very end during atmospheric entry, and the end is still days away. The lunar module is a lifeboat, but without room. Aquarius is powered up not as a home. It's powered up like a raft in the ocean. It's cramped. Everything in it is designed for two. Every instrument is not convenience. It's energy consumption. 3 people begin living the way people live on a submarine during an accident. Short commands, short breaths, short decisions. And here comes the next fork. No longer dramatic, but domestic. What can you turn off to live longer? And what can't you turn off without dying right away? In space, there is no comfort. There are functions. Ventilation is needed, so the air mixes. Heating is needed so systems and people don't freeze. Navigation is needed so you don't miss Earth. But the more you keep on, the faster you eat the batteries. And the batteries in the lunar module are not fuel cells. They're chemical batteries. They give up a stored reserve, and that's it. Bring the trajectory back under control. Even if the free return is close, that's still not a guarantee. By the time of the accident, Apollo 13 was no longer flying the ideal insurance route of loop around and come back by itself. The landing plan required corrections, and the trajectory became less self-returning. And so, Houston makes a decision that sounds dry, but in meaning is like turning a key in the lock of rescue. We perform a correction burn with the lunar module engine to restore a free return. It's a frightening decision for 2 reasons. 1, the lunar module engine is not the spacecraft's main engine, and using it as the return engine is changing a system's role on the fly. 2, the burn has to be precise, and precision depends on navigation, which they can't use normally now. Much is powered down, the platform can drift, and star sightings are obstructed by the debris and gas cloud from the service module. But there's no choice, and the crew does what in space always sounds like art. They hold the ship with their hands, by references by the sun, by simple procedures that, in a normal mission, would have been backups. The burn is short, seconds, but those seconds change days. In mission control, no one smiles at that moment. They simply note the chance has become more real. A watt, a sip, a degree. And now begins the life people rarely think of when they say heroism. A life made of constraints, energy. To survive, they have to turn almost everything off. But by turning things off, you lose heat, ventilation, the ease of orientation, water. This isn't I'm thirsty, it's physiology. And it's also cooling for some systems. Water becomes a schedule, like medicine, heat. When you save energy, the spacecraft stops being a warm home. It starts to cool, the temperature drops. Condensation appears on the panels. Inside, it becomes damp and cold, so cold that breathing feels visible, even without visible vapor. 3 people in a cramped module. And yet, it's cold, like a refrigerator, because space takes heat without mercy, and you yourself shut the heater down to survive longer. And here comes the third important decision, the most human one. We endure the cold, we save the batteries. Not because they're brave, because otherwise the batteries will run out before Earth. Why there was almost no time for mistakes. It seems like everything was decided on board, but in reality, Apollo 13 is a duet that only works as 2. The crew plus Houston. On Earth, teams calculate procedures as if they're playing chess with physics. What to turn on for 30 seconds to get the needed data, and then turn back off. How to do a correction without eating the batteries. Which instruments can be left unpowered, and what will break irreversibly because of it. And even more important, on Earth they have what the crew doesn't. Simulators. Engineers and astronauts on the ground run through the steps in advance, verify sequences, and look for where a procedure doesn't add up. This isn't romance. It's the industrial discipline of rescue. On board, it's execution. There, you can't try again. There, every step is the only one. 4th decision. Speed up the return so they don't die on the way. A free return is a chance, but the chance may be too slow. If you fly as it goes, you might get back later, and resources will run out earlier. And then comes another plot turn. Perform an additional burn with the lunar module engine to shorten the flight time and refine the atmospheric entry. It's frightening because it again spends batteries, but it can save oxygen, water, and life because it reduces the time spent in the refrigerator. Again, precision. Again, orientation under conditions where normal navigation is powered down. Again, communications and commands. And again, a short engine fire that rewrites the trajectory. Survival turns into a paradox. You spend a resource to preserve a resource. The closest view and the most distant goal. They will see it closer than many missions before them, but without any celebration. The moon is not the goal. The moon is a turning point on the road home. In this moment, there is a frightening beauty in the story. The moon's gravity works like a huge hand that turns the spacecraft back toward Earth. And the crew understands. The hardest part ahead isn't in space, it's at the end. Because at the end they will have to bring the command module back to life. That same Odyssey that is now powered down almost to zero, cold and damp like an abandoned capsule. And they will have to revive it fast, on batteries, right before re-entry. Carbon dioxide, an invisible wall. While they count water in watts, another number climbs. CO2. The lunar module is designed for 2. The filters are designed for 2. But there are 3 people. Carbon dioxide rises not like a catastrophe, but like pressure in a sealed room, slowly, inevitably. And it's dangerous precisely because it's invisible. You can't see it, but it changes breathing, consciousness, the ability to make decisions. And the ability to make decisions is the only thing separating them from the end right now. And Houston realizes they don't have days left. They have until the filters hold. And then a new task appears in Mission Control, one that sounds almost funny if you forget what's at stake. Make an adapter. Make it so the square filters from the command module work in the round system of the lunar module. Out of what's on board, cardboard, plastic, hoses, duct tape, like an engineering kit in an extreme reality. But it won't be a little clever hack. It will be a cold, verified procedure, built first on Earth and then repeated, exactly, in space. In the next part, we'll step into the mission's most famous engineering thriller, CO2 and the mailbox, and then into the final race, how they revived Odyssey, how they entered the atmosphere, and why the last minutes were uncertainty even after everything had already worked out. When air becomes a threat. Inside Aquarius, everything looks like cold weather survival, rationed water, instruments shut down, trembling fingers. But the real danger doesn't come from the walls or from the batteries. It comes from breathing. Carbon dioxide rises slowly and relentlessly. You can't see it, only read it in numbers. And those numbers begin to creep upward. The lunar module is designed for 2, but 3 are living in it. The lunar module's lithium hydroxide filters are supposed to bind CO2, but their capacity melts away faster than planned. And in Houston, they understand a simple thing. Time is now measured not in hours to Earth, but in time until too much CO2. Don't fix the ship, fix the air. The decision is phrased as if it were easy. Connect the command module filters to the lunar module system. And in that second, a problem appears that sounds almost funny, until you remember what's at stake. The command module's filter canisters are square. The lunar module's mounting points are round, literally square into round. That's not a metaphor, that's the geometry of life. Build a rescue out of what's already on board. In Mission Control, nobody says, let's do it with tape. That's not how reality works. In reality, it sounds different. What do they have on board? What materials? What hoses? What bags? What plastic pages? What fasteners? Because in space you can't send a spare part. You can't make a delivery. You can only assemble a solution from what's already flying with the crew. Engineers on Earth build a mock-up, right there, on a table, from items the astronauts really do have. Plastic bags, plastic laminated cards from onboard documentation, suit hoses, and lots of gray reinforced duct tape. It looks ugly, but this isn't a design exhibition, it's oxygen mathematics. And here again, the story of one decision shows itself. They decide not to wait, not to save an attempt, not to make sure first. They decide to build it and switch it on, because otherwise it will be too late. Building the mailbox in zero gravity and cold. Now comes the hardest part, bringing an Earth-made solution into space. Houston reads the instructions, step by step. Not more or less like this, but in a way that can be repeated exactly. The astronauts pull out the materials and begin building the device that will later be called the mailbox. There are no heroic slogans in this thriller. There are gloved hands, cold, cramped space, and a single thought. If we make a mistake, we won't be able to fix it. And when they hook the device up, something happens that rarely happens in emergencies. It works. The CO2 level stops rising the way it should have. The situation stabilizes. This isn't "we won," it's "we moved the edge back." But in space, sometimes those are the same thing. The engine that became the main one. While they're saving the air on board, people on Earth are saving the geometry of the flight. After the accident, the spacecraft had to be put back onto a free return trajectory, one where the moon's gravity would swing the coupled modules back toward Earth. And here another key decision appears, quiet but fate-defining. Use the lunar module engine as the main engine for the return. Because the service module is damaged and the command module is asleep, its batteries must be saved for re-entry. The first major burn is performed using Aquarius's engine to get a safe course home, a short impulse on the order of a few dozen seconds, enough to rewrite the trajectory. And then, another crucial move. After swinging around the moon, they fire the engine again to speed up the return, saving time and shifting the splashdown zone to a more standard Pacific area. It's the paradox of survival. You spend fuel and energy in order to spend less water, heat, and time. The closest moon they weren't flying to. They pass behind the moon. For a few seconds it looks like a space postcard, but inside, this isn't tourism. In this moment, the moon in their lives is just a gravitational turn, a huge stone that helps them get back. And still, there's an image you can't forget. They see the moon up close, and they know they won't land. Not because the mission is canceled, because the mission is different now. The mission is not to die. Odyssey has to be turned back on. They held CO2 in check. They held the trajectory in check, air, water, heat, on the edge, but still within limits. And now the final task appears, the one that makes you truly cold. The command module has to be brought back to life. Odyssey is almost completely powered down, protected like the last battery in the dark. But re-entry is impossible without it, and they'll have to revive it under conditions of cold and condensation, limited batteries, a strict power-up sequence, and very little time before entry. This isn't turning on a light. It's starting a system that must work perfectly when plasma forms outside and communications black out for minutes. A silence that lasts too long. The final hours before Earth are preparation for an exam you can't retake. Houston writes and rewrites the power-up sequence, what to switch on, in what order, how many seconds to keep it on, where to save amperes. The crew rehearses the steps by ear, like learning a melody you can't play out of tune. And then the moment of atmospheric entry comes, a fiery shell around the capsule, radio blackout, silence. And the silence is supposed to last a few minutes, but it can last too long, and that too long is the scariest minute in the whole story. In the next part, we'll live through the finale, how they powered up Odyssey, how they detached the rescue lifeboat, the lunar module, how they entered the atmosphere, and what was changed after Apollo 13 in engineering and protocols, so that such a chain of failures would never happen again. Revive a dead home. All this time, the command module Odyssey wasn't a ship, but a safe. Inside it was the most valuable thing, the batteries needed during atmospheric entry. And now comes the moment that's scarier than any trajectory correction. It has to be powered back on. Not switch on a lamp, but start a system that must withstand G-forces, plasma, loss of communications, parachute deployment, and splashdown in the ocean. The problem is that Odyssey was shut down for a long time, in the cold. Inside, dampness, condensation, instruments chilled. Outside, space, which doesn't forgive short circuits or mistakes in sequence. And again, the story of one decision. The decision sounds like this. We turn on only what's necessary to survive re-entry. Everything else, later or never. Houston writes the power-up procedure literally like open-heart surgery. In what order, in what groups, which circuits, which instruments, so they don't eat the batteries too soon. The crew repeats the steps out loud, like a prayer. Only an engineering one. Click, a light on the panel, dim but alive. Odyssey returns not at once, not joyfully, but cautiously, like someone coming to after fainting. The fifth fork, letting go of the lifeboat. The lunar module. Aquarius did the impossible. It became a home for three and the engine of their return. But at the end of the journey, it turns from salvation into risk. Because you have to enter Earth's atmosphere in the command module, and the lunar module must be jettisoned. Otherwise, it will interfere with aerodynamics and could disrupt the landing configuration. And so comes another decision that sounds like betrayal, but is in fact part of rescue. We separate Aquarius. It's psychologically hard. You lived in it through the cold days. You owe it your air and your chance. And now you have to let it go into the void. In space, it looks simple. Commands, latches, separation. Inside a person, it looks different. Like closing a door and walking away, knowing it will never open again. One image they'll remember forever. There's a moment that in stories about Apollo 13 is often told quietly. When they jettison the damaged service module, the crew sees the scale of the accident for the first time. Before that, they knew it from numbers, from leaks, from failures. Now, with their eyes, a damaged panel, the trace of destruction, a gaping wound where there should have been a smooth surface. And then it becomes clear. This wasn't a malfunction. This really was a situation where the line between they came back and they didn't ran along the thinnest edge of decisions. The re-entry corridor, a narrow slot, between too steep and too shallow. Coming back to Earth is also a choice, only one made in advance by physics. The capsule has to enter the atmosphere at the correct angle. That's called the re-entry corridor. Too steep, overheating and G-loads, a risk of breakup or going beyond calculated limits. Too shallow, the capsule can skip off the upper atmosphere and head back out into space. And that's why their whole fight over the trajectory mattered so much. Not just make it there, but make it there in a way that turns the atmosphere into a break, not a wall. Blackout re-entry begins. Outside the capsule, the air heats into plasma. Plasma isn't just hot. It's an ionized layer that shields radio signals. Communications are supposed to drop for several minutes. That's a normal part of coming home. But a normal part doesn't get easier just because you know it's normal. Houston waits, the silence lasts a minute, then two, and suddenly it stretches longer than expected. Here, this is the scariest second in the entire story, because everyone has already done everything. All decisions have been made, all procedures have been executed, and now there's only waiting for physics to speak. And finally, a voice. At first weak, then clearer. They're back on the air. In moments like that, nobody delivers a beautiful shout. Someone simply exhales, for the first time in days. Parachutes. Parachutes are always a movie shot, but for the crew, it isn't a shot. It's a sign. The atmosphere accepted them. The speed is bled off. The system is working. They're no longer falling into nothing. They're falling into Earth's air, and the ocean is not a threat. It's a soft landing pad. Spray, impact, rocking. And then, after cold, metal, and vacuum, a sound appears that can't be faked. Water against the hull. Earth. Finale. The best lesson in risk management. Why is Apollo 13 called a successful failure? Because the mission failed its original objective, landing on the moon. But it achieved a higher objective, saving people when the system is collapsing in a cascade of failures. And what matters is this. It's not a story of everyone was a genius. It's a story about an engineering culture that, in a critical moment, knows how to accept reality, there will be no moon, rebuild the objective, come back alive, and turn chaos into procedures. What did they change afterward? Not one part. More like an entire layer of thinking. They strengthened quality control and reworked the design protection of assemblies tied to the oxygen tanks and their internal components. They revised ground procedures, tests, and criteria for what counts as acceptable to reduce the chance of the failure chain repeating. They updated emergency checklists, training, and simulator scenarios, so crews in Houston could switch faster into rescue mode without losing time to guesswork. They reinforce the approach to redundancy and system independence, so one failure wouldn't turn into an avalanche. And if you translate that into the language of any team, not just a spaceflight team, risk is manageable not when everything goes to plan, but when you can rebuild the plan without losing the meaning. One choice that held everything together. If you had to pick one decision the whole story rests on, it wouldn't be about duct tape or heroic phrases. It would be this: to immediately accept that the command module wouldn't save them on the way home, and to turn the lunar module Aquarius into a lifeboat. That decision cut off the moon, but it opened up Earth. And after that, everything, rationing, burns, CO2 filters, power-up procedures, became a chain built around that one choice. Because sometimes survival isn't performing a miracle. It's choosing the right next step when every step looks bad. If this story made you feel how thin the line is between a plan and survival in space, like the video and subscribe to the channel. More real space dramas and science adventures are ahead, where every detail decides everything. Hit the bell so you don't miss the next episode.